The fundamental theorem of calculus is a theorem that links the concept of the derivative of a function with the concept of the integral. The first part of the theorem, sometimes called the first fundamental theorem of calculus, is that an indefinite integral of a function can be reversed by differentiation. This part of the theorem is also important because it guarantees the existence of antiderivatives for continuous functions. The second part, sometimes called the second fundamental theorem of calculus, is that the definite integral of a function can be computed by using any one of its infinitely many antiderivatives. This part of the theorem has key practical applications because it markedly simplifies the computation of definite integrals. History. The fundamental theorem of calculus relates differentiation and integration, showing that these two operations are essentially inverses of one another. Before the discovery of this theorem, it was not recognized that these two operations are related. Ancient Greek mathematicians knew how to compute area via infinitesimals, an operation that we would now call integration. The origins of differentiation likewise predate the fundamental theorem of calculus by hundreds of years. For example, in the 14th century the notions of continuity of functions and motion was studied by the Oxford calculators and other scholars. The historical relevance of the fundamental theorem of calculus is not the ability to calculate these operations, but the realization that the two seemingly distinct operations are actually closely related. The first published statement and proof of a restricted version of the fundamental theorem was by James Gregory. Isaac Barrow proved a more generalized version of the theorem while Barrow's student Isaac Newton completed the development of the surrounding mathematical theory. Gottfried Leibniz systematized the knowledge into a calculus for infinitesimal quantities and introduced the notation used today. Geometric meaning. For a continuous function y equals f, x, whose graph is plotted as a curve, each value of x has a corresponding area function a, x, representing the area beneath the curve between 0 and x. The function a, x, may not be known, but it is given that it represents the area under the curve. The area under the curve between x and x plus h could be computed by finding the area between 0 and x plus h, then subtracting the area between 0 and x. In other words, the area of this a sliver would be a, x plus h, a, x. There is another way to estimate the area of this same sliver. As shown in the accompanying figure, h is multiplied by f, x, to find the area of a rectangle that is approximately the same size as this sliver. So, in fact, this estimate becomes a perfect equality if we add the red portion of the excess area shown in the diagram. So, rearranging terms. As h approaches 0 in the limit, the last fraction can be shown to go to 0. This is true because the area of the red portion of excess region is less than the area of the tiny black bordered rectangle. The area of that tiny rectangle, divided by h, is simply the height of the tiny rectangle, which can be seen to go to 0 as h goes to 0. Removing the last fraction from our equation then, we have. It can thus be shown that f, x, equals or squared, x. That is, the derivative of the area function a, x, is the original function f, x. Or, the area function is simply an antiderivative of the original function. Computing the derivative of a function and or finding the r under its curve are opposite operations. This is the crux of the fundamental theorem of calculus. Physical intuition. Intuitively, the theorem simply states that the sum of infinitesimal changes in a quantity over time adds up to the net change in the quantity. Imagine for example using a stopwatch to mark off tiny increments of time as a car travels down a highway. Imagine also looking at the car's speedometer as it travels, so that at every moment you know the velocity of the car. To understand the power of this theorem, imagine also that you are not allowed to look out the window of the car, so that you have no direct evidence of how far the car has traveled. For any tiny interval of time in the car, you could calculate how far the car has traveled in that interval by multiplying the current speed of the car times the length of that tiny interval of time. Now imagine doing this instant after instant, so that for every tiny interval of time you know how far the car has traveled, in principle, who could then calculate the total distance traveled in the car by simply summing up all those tiny distances. Distance traveled equals the velocity at any instant, a tiny interval of time. In other words, distance traveled equals, on the right-hand side of this equation, as becomes infinitesimally small, the operation of summing up corresponds to integration. So what we've shown is that the integral of the velocity function can be used to compute how far the car has traveled. Now remember that the velocity function is simply the derivative of the position function. So what we have really shown is that integrating the velocity simply recovers the original position function. This is the basic idea of the theorem, that integration and differentiation are closely related operations, each essentially being the inverse of the other. In other words, in terms of one's physical intuition, the theorem simply states that the sum of the changes in a quantity over time adds up to the total net change in the quantity. Or to put this more generally, given a quantity that changes over some variable, and, given the velocity with which that quantity changes over that variable, then the idea that distance equals speed times time corresponds to the statement. Meaning that one can recover the original function by integrating its derivative, the velocity, over. Formal statements. There are two parts to the theorem. Loosely put, the first part deals with the derivative of an antiderivative, while the second part deals with the relationship between antiderivatives and definite integrals. First part, this part is sometimes referred to as the first fundamental theorem of calculus. Let f be a continuous real-valued function defined on a closed interval, a, b. Let f be the function defined, for all x in, a, b, by. Then, f is continuous on, a, b, differentiable on the open interval, and for all x in. Alternatively, if f is merely Riemann integrable, then f is continuous on, a, b. Corollary, the fundamental theorem is often employed to compute the definite integral of a function f for which an antiderivative f is known. Specifically, if f is a real-valued continuous function on, a, b, and f is an antiderivative of f in, a, b, then the corollary assumes continuity on the whole interval. This result is strengthened slightly in the following part of the theorem. Second part, this part is sometimes referred to as the second fundamental theorem of calculus or the Newtonian-Leibniz axiom. Let f and f be real-valued functions defined on a closed interval, a, b, such that the derivative of f is f. That is, f and f are functions such that for all x in, a, b. If f is Riemann integrable on, a, b, then the second part is somewhat stronger than the corollary because it does not assume that f is continuous. When an antiderivative f exists, then there are infinitely many antiderivatives for f, obtained by adding to f an arbitrary constant. Also, by the first part of the theorem, antiderivatives of f always exist when f is continuous. Proof of the first part, for a given f, t, define the function f, x, as for any two numbers x1 and x1 plus ix in, a, b, we have and. Subtracting the two equalities gives. It can be shown that the sum of the areas of two adjacent regions is equal to the area of both regions combined. Manipulating this equation gives. Substituting the above into results in. According to the mean value theorem for integration, there exists a real number in x1, x1 plus ix, such that. To keep the notation simple we will continue writing c instead of but one should keep in mind that c does depend on. Substituting the above into we get. Dividing both sides by ix gives. The expression on the left side of the equation is Newton's difference quotient for f at x1. Take the limit as ixa 0 on both sides of the equation. The expression on the left side of the equation is the definition of the derivative of f at x1. To find the other limit, we use the squeeze theorem. The number c is in the interval, x1, x1 plus ix, so x1 a per mole currency c a per mole currency x1 plus ix. Also, and, therefore, according to the squeeze theorem. Substituting into, we get. The function f is continuous at c, so the limit can be taken inside the function. Therefore, we get. Which completes the proof. Lighthold al., 1996, proof of the corollary. Suppose f is an antiderivative of f, with f continuous on a, b. Let. By the first part of the theorem, we know g is also an antiderivative of f. Since fg equals 0, the mean value theorem implies that f, g is a constant function, i.e. there is a number c such that g, x, equals f, x, plus c, for all x in a, b. Letting x equals a, we have. Which means c equals f, a. In other words g, x, equals f, x, af, a, and so. Proof of the second part. This is a limit proof by Riemann sums. Let f be integrable on the interval a, b, and let f admit an antiderivative f on a, b. Begin with the quantity f, b, af, a. Let there be numbers x1, xn such that it follows that. Now, we add each f, xi, along with its additive inverse, so that the resulting quantity is equal. The above quantity can be written as the following sum. Next, we employ the mean value theorem. Stated briefly, let f be continuous on the closed interval, a, b, and differentiable on the open interval. Then there exists some cn such that it follows that the function f is differentiable on the interval, a, b. Therefore, it is also differentiable and continuous on each interval, xi1, xi. According to the mean value theorem. Substituting the above into, we get. The assumption implies also, can be expressed as a partition. We are describing the area of a rectangle, with the width times the height, and we are adding the areas together. Each rectangle, by virtue of the mean value theorem, describes an approximation of the curved section it is drawn over. Also need not be the same for all values of I, or in other words that the width of the rectangles can differ. What we have to do is approximate the curve with n rectangles. Now, as the size of the partitions gets smaller and n increases, resulting in more partitions to cover the space, we get closer and closer to the actual area of the curve. By taking the limit of the expression as the norm of the partitions approaches 0, we arrive at the Riemann integral. We know that this limit exists because f was assumed to be integrable. That is, we take the limit as the largest of the partitions approaches 0 in size, so that all other partitions are smaller and the number of partitions approaches infinity. So, we take the limit on both sides of. This gives us neither f, b, nor f, a, is dependent on, so the limit on the left side remains f, b, af, a. The expression on the right side of the equation defines the integral over f from a to b. Therefore, we obtain. Which completes the proof. It almost looks like the first part of the theorem follows directly from the second. That is, suppose g is an antiderivative of f. Then by the second theorem. Now, suppose. Then f is the same derivative as g, and therefore phi euro squared equals f. This argument only works, however, if we already know that f has an antiderivative, and the only way we know that all continuous functions have antiderivatives is by the first part of the fundamental theorem. For example, if f, x, equals ax2, then f is an antiderivative, namely. And there is no simpler expression for this function. It is therefore important not to interpret the second part of the theorem as the definition of the integral. Indeed, there are many functions that are integrable but lack antiderivatives that can be written as an elementary function. Conversely, many functions that have antiderivatives are not Riemann integrable. Examples: as an example, suppose the following is to be calculated here, and we can use as the antiderivative. Therefore. Or, more generally, suppose that is to be calculated here, and can be used as the antiderivative. Therefore. Or, equivalently. Generalizations: we don't need to assume continuity of f on the whole interval. Part 1 of the theorem then says, if f is any Lebesgue integrable function on a, b, and xo is a number in a, b, such that f is continuous at xo, then is differentiable for x equals xo with phi euro squared, xo equals f, xo. We can relax the conditions on f still further and suppose that it is merely locally integrable. In that case, we can conclude that the function f is differentiable almost everywhere and phi euro squared, x, equals f, x, almost everywhere. On the real line this statement is equivalent to Lebesgue's differentiation theorem. These results remain true for the Henstocker-Euro-Kurzweil integral, which allows a larger class of integrable functions. In higher dimensions Lebesgue's differentiation theorem generalizes the fundamental theorem of calculus by stating that for almost every x, the average value of a function f over a ball of radius are centered at x tends to f, x, as a tends to 0. Part 2 of the theorem is true for any Lebesgue integrable function f, which is an antiderivative f. In other words, if a real function f on a b admits a derivative f, x, at every point x of a b, and if this derivative f is Lebesgue integrable on a b, then this result may fail for continuous functions f that admit a derivative f, x, at almost every point x, as the example of the Cantor function shows. However, if f is absolutely continuous, it admits a derivative phi euro squared, x, at almost every point x, and moreover phi euro squared is integrable, with f, b, a equal to the integral of phi euro squared on a b. Conversely, if f is any integrable function, then f as given in the first formula will be absolutely continuous with phi euro squared equals fae. The conditions of this theorem may again be relaxed by considering the integrals involved as Henstocker-Euro-Kurzweil integrals. Specifically, if a continuous function f, x, admits a derivative f, x, at all but countably many points, then f, x, is Henstocker-Euro-Kurzweil integrable and f, b, a, is equal to the integral of f on a b. The difference here is that the integrability of f does not need to be assumed. The version of Taylor's theorem, which expresses the error term as an integral, can be seen as a generalization of the fundamental theorem. There is a version of the theorem for complex functions. Suppose U is an open set in C and phi U C is a function that has a holomorphic antiderivative f on U. Then for every curve I cubed a, b, a U, the curve integral can be computed as. The fundamental theorem can be generalized to curve and surface integrals in higher dimensions and on manifolds. One such generalization offered by the calculus of moving surfaces is the time evolution of integrals. The most familiar extensions of the fundamental theorem of calculus in higher dimensions are the divergence theorem and the gradient theorem. One of the most powerful statements in this direction is Stokes' theorem: let M be an oriented piecewise smooth manifold of dimension n and let B in one form that is a compactly supported differential form on M of class C1. If M denotes the boundary of M with its induced orientation, then here D is the exterior derivative, which is defined using the manifold structure only. The theorem is often used in situations where M is an embedded oriented submanifold of some bigger manifold on which the form is defined. See also differentiation under the integral sign. Notes: more exactly, the theorem deals with definite integration with variable upper limit and arbitrarily selected lower limit. This particular kind of definite integration allows us to compute one of the infinitely many antiderivatives of a function. Hence, it is almost equivalent to indefinite integration, defined by most authors as an operation that yields any one of the possible antiderivatives of a function, including those without a zero. Spivak, Michael, Calculus, Houston, Texas, Publish or Perish Incorporated. C. For example, Marlowe Anderson, Victor J. Katz, Robin J. Wilson, Sherlock Holmes in Babylon and Other Tales of Mathematical History, Mathematical Association of America, 2004, pages 114. http www.archive.org Baruoft, Baz, Lippmann. Calculus, pages 180 to 181. Apostle 1967, A Section 5.1, Apostle 1967, A Section 5.3, Spivak, Michael, Calculus, Houston, Texas, Publish or Perish Incorporated. Rudin 1987, th 7.21, References, The Postal, Tom M., Calculus, Volume 1, One-Variable Calculus with an Introduction to Linear Algebra, New York, John Wiley & Sons, ISBN A978-0-471-00005-1A. Bartle, Robert, A Modern Theory of Integration, AMS, ISBN A0-8218-0845-1A. Larson, Ron. Edwards, Bruce H. Head, David E., Calculus of a Single Variable, Boston, Houghton Mifflin Company, ISBN A978-0-618-14916-2A. Leithold, L., The Calculus of a Single Variable, New York, HarperCollins College Publishers. Mallett, A., Studies on James Gregory. Rudin, Walter, Real and Complex Analysis, New York, McGraw-Hill Book Company, ISBN A0-07-054234-1. Stewart, J., Fundamental Theorem of Calculus, Calculus, Early Transcendentals, Belmont, California, Thomson Collier. Turnbull, H. W., ed., The James Gregory Tercentenary Memorial Volume, London. Spivak, Michael, Calculus, Houston, Texas, Publish or Perish Incorporated. A. Caron, Richard. John, Fritz, Introduction to Calculus and Analysis, Springer. Further reading, Hernandez Rodriguez, O.A. Lopez Fernandez, J.M. Teaching the Fundamental Theorem of Calculus, A Historical Reflection, Loci, Convergence, January 2012. External links, Haswinkel, Mikhail, ed., Fundamental Theorem of Calculus, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. James Gregory's Euclidean Proof of the Fundamental Theorem of Calculus at Convergence, Isaac Barrow's Proof of the Fundamental Theorem of Calculus, Fundamental Theorem of Calculus at immermath.com.